All right, you guys, I want to just wrap this up for us taking a look at this lab that you were looking at. So, this is, for those of you recognize and those of you don't, this is data I took from someone in period 7-8, and I'm using it because it's a good representation of what you should have seen happen. So if you kind of take a look, let me just sort of make this a little bit neater here for a second. Here's what this data represented for this particular class. It's the same data that everyone took. These are our masses in grams. But when they took this final mass here, they did not include the small beaker. So in order for us to compare apples to apples, if I were to add the two masses, and we're talking system 3, we've already talked about system 1 and 2. If we were to add those two masses together, see, now I just erased it. I should get my calculator so that I actually know. All right, here's my calculator. When I add those two together, I get 53.82 plus 130.05. Whoops. I get 183.87 grams. Well, that obviously doesn't match up with 153.51 grams, but what we have an issue with here is that we didn't include the small beaker. So we're going to subtract out the mass of the small beaker, so minus 30.25 grams, and we get 153.62 grams is what the beaker should have massed based on the before the reaction, and this is what it massed when it was done for real. And so you can see that these numbers are really pretty good. I mean, certainly there may have been a little liquid caught in the flask or whatever. So when we go scroll down to this, we answered some of these questions earlier, but system 3, is mass conserved? Yes. Now I don't know if your data shows that, but it should have. Chemical or physical change, you might want to consider what you put here. You poured two clear colorless liquids together and you should have gotten a milky white substance. And if you let it sit for a while, you probably saw that the white stuff fell to the bottom. You actually made a white solid. You didn't have that before. You made some new substance. That's not a physical change. That's a chemical change. That white powder really told us that. I'm not going to deal with the conservation of mass from system 1 because some of your numbers turned out, or on the volumes turned out a little wacky. But let's just talk about these other two. This is what I did in class. I hooked up that flask and beaker and stopper and Alka-Seltzer, and we saw that in the beginning it was heavier, and in the end it was lighter. And then we use that to actually compute the density of a gas. So when we go back to looking, is mass conserved? It lost mass. So maybe it's not. But here's what I'm wondering, and I don't know how your numbers turned out exactly, but when you look at system 2, and it depends how good you were with this, you had your Alka-Seltzer tablet and a small amount of water, and then when you put it in the balloon, there's your little water, when you put the tablet in the balloon, you're supposed to pinch it off immediately. Now, I don't know how good you were, but of course the balloon got a little bit bigger as you saw that happening. Why? Because the carbon dioxide was being given off. But the difference here, and I hope that you can see it, the difference here was that we were trying to trap the carbon dioxide. So depending on how good your numbers were determines how great it is. So what I'm curious and what you ought to do is to take your two numbers here and compare it to your number here and ask yourself the question, should they be the same if you trap the carbon dioxide? Or should they be different? If all went well, with no error, they should have been the same. Now, I don't know how your numbers turned out, but take a look and see. You'll be able to tell if you were experts at this or not. If you were an expert, they should have been pretty gosh darn close. If you weren't, you may have, some of you, in the tying process, may have lost a little carbon dioxide, and if you did, I would have expected this number to be a little bit less. But so system 4 in general, is mass conserved? Yes, if you're really good. But then why did this one get smaller? It lost mass. But did it really lose mass? If the carbon dioxide left, is that mass simply gone? Or if we had somehow managed to trap it, could we account for that mass? And the answer is yeah, if we could have trapped this gas, we could have accounted for that mass. So mass is conserved. So here's some really crucial stuff, you guys. Is there a law of conservation of volume? The answer is absolutely positively not. We did not conserve volume. We talked about this in class. With the ethanol and the water, one fit into the spaces. We didn't add 50 and 50 and got 100. We got 50 and 50 and got 97. It's the new math. Because there is no law of conservation of volume. Can volume be conserved? Yeah, if you added water and water, it could be. But is there a law, something that for sure says that the volume is always conserved? The answer is no. But is there a law of conservation of mass? Yes, 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 there is. Okay? Anytime you have a reaction from the beginning to the end, or a physical change, or a chemical change, it doesn't matter. If you're really good at collecting your numbers, like here, I wonder, were you really good? If you're really good at collecting your numbers, there should be no change in the mass at all. So, hope that helps. Bye, guys.